Alright, we're going to use SketchUp here to just demonstrate the kind of simple mathematics and the graphics that you can use to solve a circular dam gate problem. You'll see a couple of those at the end of chapter 3. And the reason they're in there is to kind of show you, I think if nothing else, a little bit of elegant engineering, why those dam gates are shown, are often built with a curvature to them. And it has to do with the difference between a force or pressure whose line of action goes through the spinny point or the point of pivot, and a straight gate where each of the pressures actually acts as a resistance to spin. So it's trying to, it makes it harder to spin the gate. So just to demonstrate that, I'm going to get rid of Lance here, and I'm going to erase him. And I'm just going to start by drafting a box like we often do if we're drafting in 3D. I'm going to make it, I'll make it 100 feet, comma, 100 feet. It's a big box. We'll make it a little bit smaller here in a little bit. And I'm going to move my hand over here. I'm starting to try to use the shortcut, but I won't do them today. I'll push that up about 30 feet. And I'll now draft in just a circle here. That will kind of make something like that. We'll go ahead and move the circle. I'm hitting a control key and using the move button here. Control, you'll see, actually does a copy in SketchUp. So, and my goal here is not to so much show SketchUp, but it's a little bit easier to draft the concepts here. So let's assume now that actually, in all actuality, the dam gate was more something like, use an offset here, it's F. Let's say the dam gate was something like that. And it went someplace straight across there. And so that became more or less the gate. And we'll see me make it now in 3D. The gate, something like that, from there to there. And go ahead and get rid of a bunch of this stuff now. Now all I've got is essentially this little bit here, this kind of wall. And we're drafting, as you see, in cross section. What I'm going to do now is to make that, I'll make it just 1 foot, as we've seen in the past. We do our calculations very often on 1 foot. Do that, push it, 1 foot. So I essentially, that's no good. Let me go back, edit, undo, control Z. I'm going to push it out more like 10 feet so you can see it, 10. Alright, so here's what we have when we're looking at something like that. Let's assume now that, like I said, that the ground elevation is something more like here. In other words, the ground of the water is somewhere out along there. Something. I guess I'll do it this way. And I'll push it out. So that's the ground. Get rid of a few more of these here. And we've got the dam gate. And let's assume there's a water surface up about, I don't know, about a few feet higher. Maybe make it at the top of the gate. Hitting a control key here. Taking it up to the top, more or less. And I can now move this here. And I'm hitting a control key. Control, you'll see very often in SketchUp, if you're moving things, you've got to use the control key, because if you don't, you drag everything along with it. So right there, all I wanted to do was kind of fill in my water surface there. And I'll finally go ahead and paint up my water surface. Hopefully with the paint bucket tool. Alright, so we've got some water on top of the dam. Now, why the round gate? And what are we doing with the roundness? Well, mathematically what you're doing when you're trying to calculate these is you're trying to break them up into pressure surfaces and weight surfaces that you can kind of understand. So I'll do that next here by going ahead and doing a section through here. Kind of going to see me push through. Kind of draw that in cross section here. And if you think about it, if we're going to go ahead and draft this up, straight up here, we've actually got a triangular pressure surface that looks something like this, right, that we can calculate by taking, right, this and drawing a resultant someplace in the order of something like that, right? The resultant would be a third from the bottom, third from the heavy end. It's a triangle, right? It's a resultant. It's a resultant, so it would have two hatches. If you can draw them, probably can't. Okay, you got a resultant there. You've got nothing on top here because it is a free surface, but if it was down deeper underwater, you would actually have a pressure surface that would be a rectangle, and you could draw its resultant someplace there, right, acting down. If you knew how to draw. Okay, you got a resultant there. And then finally what you have is right in here you have essentially a weight surface that's a little bit harder to calculate. But it does have an area and it has a density, and so you could also determine a resultant down someplace down here, right? Heading down, if you could, go down. You could actually draft a vector here, a vector here, and a vector here. Well, that's all well and good. And if you think about the free body now being essentially the line here, down, and then the dam, you now have summarized all of the hydrostatic forces acting on that dam. Here's the fun part about a circular gate, however. All of the individual forces that are pushing on this gate, all of the individual pressures, have to act normal to the gate. That's the definition of pressure with the fluid when a fluid interfaces with the surface. And so what you have is a whole bunch of forces and pressures that are acting through the center of the circle, which means they have no torque or moment. At the same time, the resultant of the three forces, this force here, which was the kind of resultant of the triangular pressure, this force here if you had any kind of effective overburden from water above, and then the force due to the weight acting on this kind of semicircular triangle here. If you add up those three forces tip to tail, they will have a direction, right? Because forces have magnitude and direction. When you add them tip to tail, they'll have a direction, and that direction has to go through the center of the circle because of the definition of how pressure affects each one of these, how a pressure affects when a surface, a hard surface is involved. And so by adding those three up and then using a little geometry, you can determine exactly where the center of pressure is through here, because you'll know their direction, and the direction has to go through the center of the circle. So that's probably best done graphically in a 2D world where you draw the cross section, you draw up each of these resultants, and then you use the mass prop or some other way to get essentially the centroid of a more or less the outside of a fillet here. So there are tables for that, but you can't beat mass prop to get the centroid of a shape. So by adding the resultant of the triangular pressure distribution, the resultant of the weight, and the resultant of the potential if you had any kind of overburden above, you add those three vectors together. That gives you a magnitude and a direction. You just do that so it runs to the center of the circle, and you solve the center of force, or the center of the hydrostatic pressure. So pretty rough use of SketchUp here. Really nice practice, however, when you take and start throwing this into a program like Fun Physics or anything like that, if indeed the fluid works for you. Here if you were going to do this within Sketchy Physics, you have to make a bunch of balls. You'd have to go to a more extensive modeling program like COMSOL. So again, we just saw a quick demonstration, not a great one, of kind of what a circular dam gate would look like. We've got them on the Wisconsin River. We've got amazingly huge ones in the Netherlands, because for them, a failure of their system more than once every millennia is not okay. Thanks for listening. We'll post this out and we'll talk about it in class.